AI-first data infrastructure. The self-optimizing data platform. Welcome to data superiority. In this text, we explore a concept that is likely to define the next decade of data engineering and analytics. AI-first data infrastructure, or in other words, the self-optimizing data platform. Today, most organizations operate with human-orchestrated, tool-driven data stacks. Data engineers manually design and tune pipelines. Platform teams manually configure storage classes, indexing strategies, and partitioning. Analytics engineers rewrite queries and models as usage evolves. The control plane of the platform is fundamentally human. An AI-first data platform looks very different. In an AI-first world, the platform itself continuously observes, learns, and intervenes in its own behavior. It auto-tunes resource allocation based on workload characteristics, adjusts physical data layouts in response to query patterns, and proactively detects data quality drift, semantic inconsistencies, and performance regressions. It recommends or even applies changes to schemas, indexes, caching layers, and pipeline scheduling. The end state is a cybernetic data platform, a system with feedback loops that connect observability and actuation, with AI models embedded directly in that loop. To understand this precisely, we need a rigorous definition of what AI-first data infrastructure actually means. In this text, AI-first data infrastructure is characterized by three properties: autonomic behavior, model-mediated decision-making, and closed feedback loops over operational and semantic telemetry. Autonomic behavior means the system can configure, heal, optimize, and protect itself with minimal human intervention. In the data platform context, this includes auto-scaling and auto-tuning based on workload characteristics rather than static thresholds, self-healing pipelines that detect and remediate certain classes of failure, and continuous optimization of physical design such as file sizes, partitioning schemes, clustering, and caching. The key point is that these decisions are not hard-coded heuristics. They are learned behaviors. Model-mediated decision-making means that learned models sit in the control plane and influence operational choices. This includes predictive models for workload forecasting, estimating which queries will run when and on which datasets. It includes cost models that estimate the marginal cost of running a query under different physical plans or cluster configurations. It includes policy models that decide when and how to adjust knobs like concurrency limits, cache eviction policies, or compaction thresholds. Instead of sequences of human-written if-else rules, you have models trained on historical telemetry making real-time policy decisions, often under explicit service-level objectives for latency, throughput, cost, and freshness. Closed feedback loops mean the platform continuously collects telemetry, feeds it into models, takes actions, and then measures the consequences of those actions, closing the loop. Telemetry covers query plans and runtimes, data volumes and cardinality distributions, data quality metrics, schema changes, and user interaction patterns such as dashboards viewed and pipelines triggered. Models consume this telemetry, propose actions such as repartitioning a table, moving a dataset to a different storage tier, adjusting cluster size, or quarantining a dataset that behaves anomalously. The results of these actions feed back into the telemetry so that the models can learn whether their decisions improved or degraded performance under the current conditions. To see why this matters, it helps to look at the evolution of data platforms in three broad phases. The first phase is the classic enterprise data warehouse era. Rigid schemas, heavy ETL expressed in stored procedures or proprietary tools, nightly or weekly batch loads, and manual performance tuning by DBAs. Observability is limited, and the control plane is entirely human. The second phase is cloud-native, but still human-orchestrated. Storage and compute become elastic. Data lakes and cloud warehouses decouple compute from storage, and orchestration tools, catalogs, lineage systems, and data quality frameworks emerge. There is more automation in the form of scheduled jobs and auto-scaling, but policies are still mostly static. You can think of this as the scripted automation era. The third phase, which is only beginning to emerge, is where AI models become first-class citizens in the control plane. The system does not merely observe metrics, it models them. It does not only schedule jobs on static schedules, it adapts those schedules to data arrival patterns and business cycles. It does not design partitioning strategies once, it learns partitioning strategies from access patterns and adjusts over time. It does not only emit alerts, it runs anomaly detection models continuously on telemetry. In this phase, the data platform increasingly resembles an autonomous system rather than a static piece of infrastructure. Architecturally, it is useful to decompose an AI-first data platform into three planes: the data plane, the control plane, and the intelligence plane. The data plane is the layer where data is stored and processed. This includes storage layers, such as object stores and distributed file systems, file formats, such as Parquet, ORC, Delta, or Iceberg, compute layers like distributed query engines, streaming processors, and ML pipelines, and serving layers for BI dashboards, feature stores, and analytical APIs. In an AI-first platform, the data plane must be programmable and actuatable so that the control plane can trigger compaction jobs, alter partitioning, change cluster sizes, and modify caching policies. The control plane is where policies are encoded and operations orchestrated. This includes schedulers, orchestrators, access control, governance, catalog services, and monitoring and alerting systems. In an AI-first setting, the control plane evolves into a policy engine with explicit objectives. Minimize cost subject to latency constraints. Maintain freshness for critical datasets. Enforce data quality thresholds. Balance workloads across clusters, and so on. The control plane must be able to query telemetry, invoke AI models, and issue actions to the data plane. The intelligence plane is where models live that inform the control plane. Here we find predictive models for workload and resource demand, data quality anomaly detectors, recommendation models for schema design, indexing and materialization, and reinforcement learning agents that learn control policies over time. The platform becomes both provider and consumer of machine learning. The intelligence plane consumes metadata from catalogs, lineage graphs, logs, traces, cost and billing data, and user behavior logs from BI and downstream applications. It must be tightly integrated with the control plane, but modular enough that models can be trained, versioned, and updated independently. With this architecture in mind, we can describe the core capabilities that distinguish AI-first data infrastructure from traditional stacks. The first capability is self-tuning resource management. Instead of static cluster sizes and manually configured concurrency parameters, the platform uses models to forecast workloads over time, capturing daily and weekly seasonality and special events. To predict resource demands of queries based on features such as input size, join structure, and historical runtimes. And to adjust cluster sizes, concurrency limits, and admission control policies in near real time. This can be framed as an online optimization problem. Minimize cost subject to explicit service level objectives for latency and throughput. Technically, this involves time series models for workload forecasting, supervised regression models for query cost estimation, and reinforcement learning agents that adjust control knobs based on observed performance and costs. The second capability is adaptive physical design. Most warehouses and lakes today use a fixed partitioning strategy and a few manually chosen sorting or clustering keys. In an AI-first platform, the system continuously analyzes query predicates and join conditions, empirical distributions of key columns, and the frequency and recency of accesses to different partitions. Based on this, it proposes or applies changes such as repartitioning a table on a different key or composite key, creating or dropping secondary indexes, reclustering data to co-locate frequently joined tables, and adjusting file sizes for scan efficiency. This is adaptive physical design or self-tuning storage, ongoing design space exploration guided by cost models and workload analytics. The third capability is automated data quality and semantic anomaly detection. Instead of checking only simple indicators such as row counts and null ratios, an AI-first platform learns baselines for statistical properties of columns, including distributions, correlations, and seasonality. It detects schema drift, not just in terms of fields appearing or disappearing, but also semantic drift, such as changes in units or encodings. It operates on the data lineage graph to propagate quality signals and estimate downstream impact. When a critical dimension suddenly collapses from many categories to one, the system flags this as anomalous and identifies which dashboards, reports, and ML models depend on it. This involves multivariate anomaly detection, graph propagation over lineage DAGs, and semi-supervised outlier detection techniques. The fourth capability is intelligent orchestration and scheduling. In most platforms today, pipelines are driven by static schedules, hourly, daily, or triggered by simple events like files landing. An AI-first scheduler learns dependencies and critical paths automatically from historical runs and lineage, prioritizes high-value jobs when resources are constrained, delays or batches low-priority jobs when capacity is limited, and triggers jobs based on data readiness signals rather than fixed clocks. This is closely related to dynamic DAG scheduling and priority-aware resource sharing in distributed systems, and it yields lower latency for high-value workloads with better overall utilization. The fifth capability is semantic assistance for data consumers. With a rich metadata graph and telemetry about how people query and use data, the platform can suggest relevant data sets for a particular analytical intent, recommend joins and aggregation patterns, explain lineage and provenance for fields and metrics, and flag potentially misleading metrics or incompatible aggregations. This results in a context-aware, schema-aware copilot for analytics, built on top of the same intelligence plane that drives self-optimizing behavior. Under the hood, none of this is magical. It is the composition of several algorithmic building blocks. Reinforcement learning provides a framework for control tasks such as resource allocation, where the platform observes a state describing workload intensity, queue lengths, SLO violations, utilization, and cost accumulation, takes actions such as resizing clusters or changing concurrency, and receives rewards based on performance and cost. Over time, a policy is learned that maps states to actions to maximize cumulative reward. Bayesian optimization is useful for configuration tuning. Data platforms expose many continuous and discrete parameters: file size targets, compaction thresholds, caching TTLs, join algorithm preferences, auto vacuum frequencies, and so on. Evaluating each configuration is expensive because it requires running workloads and measuring performance. Bayesian optimization maintains a surrogate model of the performance function over the configuration space and uses it to select promising configurations to evaluate next, balancing exploration and exploitation. Graph-based reasoning is essential for operating on metadata and lineage. Modern catalogs and lineage systems define a knowledge graph over datasets, columns, pipelines, reports, and owners, with edges representing derivation, joins, usage, and production relationships. Graph algorithms and, potentially, graph neural networks can be used to propagate quality signals, identify communities of related assets, recommend join paths, and quantify the impact radius of schema changes. This knowledge graph becomes the semantic substrate for AI-assisted governance and analytics. To make this more concrete, consider a few everyday scenarios. In the first scenario, a critical events table powers product analytics. Over time, the workload changes. New funnels are analyzed, different columns appear in filters and group bys, and the distribution of countries or devices shifts. In a traditional platform, performance slowly degrades unless someone manually revisits partitioning, clustering, and indexing. In an AI-first platform, the system monitors query predicates, joins, and scan patterns, observes that most queries now filter on certain columns, uses its cost model to estimate the impact of different layouts, and proposes a new partitioning and clustering strategy. It can run a background migration on a copy, compare performance before and after, and then switch over if the new design is beneficial. In the second scenario, a dimension table containing customer segments feeds numerous dashboards. An upstream mistake collapses all customers into a single segment. In a naive platform, this silent corruption propagates into reports. In an AI-first platform, the quality monitoring layer sees a sharp drop in entropy for the segment column, flags this as anomalous, and uses the lineage graph to identify impacted downstream assets. Depending on policy, it can quarantine the new partition, block downstream refreshes, or mark affected dashboards as suspect while notifying owners with a ranked set of likely root causes. This drastically reduces time to detection and limits the blast radius of data incidents. In the third scenario, during peak hours, the compute cluster is oversubscribed. Ad hoc queries, scheduled ETL, training jobs, and BI refreshes all compete for resources. With static rules, high-priority workloads can be starved or everything slows down. In an AI-first platform, the scheduler understands business criticality from metadata tags and usage patterns, predicts that SLOs will be violated under current conditions, dynamically increases the priority and resource share of high-value jobs, such as core revenue dashboards, and defers or throttles low-value workloads. It may also suggest rescheduling windows for certain pipelines based on historically low contention periods. There are, of course, serious risks and failure modes. One risk is opacity. If the control plane is driven by learned models, it can be difficult for humans to understand why a particular action was taken, why a table was repartitioned, why a job was deprioritized, or why a dataset was quarantined. Without explanations, trust erodes, and engineers may try to bypass automation. This motivates the need for interpretable models, policy logging, and mechanisms for explaining actions in human terms. Another risk is unstable feedback loops. Poorly designed feedback loops can oscillate or diverge. If a model makes a poor decision, under-provisions resources, and then learns from the degraded metrics, it may reinforce harmful behavior. Guardrails and constraints on actions, safe defaults, rollback mechanisms, staged rollout of new policies, and human oversight on high-impact actions are essential. A third risk is misaligned optimization objectives. If the system is tuned purely to minimize cost, it may degrade performance unacceptably. If it is tuned exclusively for latency, costs may explode. Objectives must be explicitly multi-objective, with constraints and priorities by dataset, workload, and business domain. Designing appropriate reward functions and policy constraints is a core challenge, not an afterthought. A fourth risk is over-delegation. If data teams accept every AI-generated recommendation uncritically, they can lose situational awareness of their own platform. An AI-first platform should augment human judgment, not replace it. In particular, changes that affect semantic meaning, such as business logic or metric definitions, should have higher levels of scrutiny and human review. For practitioners, the question is how to start moving toward AI-first infrastructure without attempting to rebuild everything at once. The first pragmatic step is instrumentation and telemetry. Without rich telemetry, no intelligent control is possible. This means capturing query plans, run times, input sizes, error types, dataset volumes, freshness indicators, quality metrics, lineage, and usage patterns. The second step is to treat metadata and lineage as a first-class graph. Assets, owners, domains, and dependencies should be explicitly modeled. Criticality levels, SLOs, and data classifications should be attached as attributes. This enables future graph-based reasoning for impact analysis and recommendations. The third step is to start with narrow, high-value control loops rather than trying to automate everything. This might be automatic detection and quarantine of anomalous partitions in a single critical dataset, an auto-scaling policy for one workload class backed by a simple forecast model, or index and materialization recommendations for a single important BI use case. Each such loop can be treated as an experiment with clear success metrics. The fourth step is to keep humans in the loop for high-impact actions, at least initially. The platform can detect problems, propose remediations, and simulate outcomes, but changes with high potential impact on semantics or user experience should require explicit approval. Over time, as understanding and trust grow, some actions can migrate to full automation. For data engineers, the shift is from handcrafting pipelines and low-level tuning to designing feedback systems and specifying high-level control policies. Instead of manually tuning Spark configurations, hand-coding backfills, and writing static DAGs, engineers define SLOs and policies, expose the right telemetry and labels, curate the metadata graph, and review higher-risk AI-driven changes. For data analysts, engines become faster and more predictable. Catalogs become semantic navigators rather than static inventories, and tools provide assistive suggestions for queries and joins. Analysts will need to understand that some recommendations are probabilistic, learn how to interpret data quality warnings and lineage overlays, and learn how to express analytical intent in ways that the system can exploit, for example by tagging metrics and dashboards with purpose and criticality. A new specialization may emerge at the intersection. A platform intelligence engineer who owns the models that power the platform itself works at the intersection of MLOps and data platform engineering and designs and monitors the feedback loops that make the infrastructure self-optimizing. To recap, an AI-first data infrastructure is a platform that observes itself through rich telemetry and metadata, learns from that telemetry using predictive models, anomaly detectors, and control policies, acts on the data plane by changing resource allocations, physical design, orchestration, and semantic assistance, and closes the loop by evaluating the impact of those actions and refining its behavior over time. It can be decomposed into a data plane, a control plane, and an intelligence plane. It uses reinforcement learning for control, Bayesian optimization for configuration tuning, and graph-based reasoning for metadata and lineage. This is not a superficial add AI to your stack story. It is a shift in how data platforms are conceived and operated. For the people building and using these systems, it means fewer manual fire drills and more work on SLOs, semantics, and feedback system design. It also opens new opportunities to apply advanced machine learning not only to business use cases, but to the data platform itself.